What and why fuel cell micro-cogeneration, heating and powering your home? It's a very simple concept, just like cogeneration, except for in the case of fuel cell micro CHP, we currently take gas from the grid or as a fuel, and that fuel is then converted into hydrogen, which is run through the fuel cell, which then simultaneously produces heat and electricity, and it's one of the most efficient ways to utilize hydrogen in a fuel cell. So the total system efficiency can reach up to 95%, depending on the technology, and you have electrical efficiency up to 60% again, depending on the various different technologies that are available on the market today. And so why does one choose, or would one choose to install a fuel cell micro CHP in their home or small business? There are many different reasons. One of them obviously is reducing CO2 emissions up to a third, saving primary energy, operating natural gas, and in the future directly hydrogen. It's producing and delivering on-site energy, so decentralized, so you're providing your own heat and electricity without having to rely too much on other external sources. And of course, it covers a higher demand for electricity. My next slide will give you an overview about the PACE project itself. It's a pan-European project. It's, as I mentioned at the beginning, it's co-funded by the EU through the FCHAU, so the Fuel Cell Hydrogen Joint Undertaking. It is a 100 million euro project, and about a third of that is provided through EU public money. The rest is provided by the manufacturers themselves in the project. There are 9 different partners. They represent the manufacturers, the OEMs, utilities, and the research community. And the objective of the project is to install up to 2,800 fuel cell micro CHP units by the end of the project, so by the end of 2021, and possibly even more. Plus or minus, each manufacturer will install 500 systems, some older generations and some newer generations. The focus is Europe, but there are 10 countries where the units are being installed, and then 4 countries have been selected to focus on more specifically in terms of policy and market development, and they are Belgium, Italy, the Netherlands, and the UK. And it's a 5-year project, began in June 2016 and will end next year. So the manufacturers you can see below in the slide, we have Solid Power, we have Bosch, Sunfire, Viessmann, and BDR Tremé, and they represent the main players in the fuel cell market today in Europe. Cogen Europe, whom I'm representing, I'm the managing director from Cogen Europe, and we are the coordinator and dissemination partner, but we're also responsible for activities related to communications and policy. And then we have 3 research partners also supporting the project: Element Energy, DTU, which is the Danish Technical University, and also the Technical University of Lausanne in Switzerland. The overall aim of the project is really to ramp up the technology and bring it to full volume commercialization, with the aim to be installing up to 10,000 units a year following the end of the project. So here's an overview of the systems that are being used in PACE. You have solid oxide fuel cells, you have PEMs, which are proton exchange membranes. These are the 2 main technologies, and Jan Willem from Solid Power will speak a little bit more to the technologies available, but more specifically to the solid oxide side, which his company is more involved in. You can see there are different sizes, different outputs, different technologies, different manufacturers across the supply chain in Europe and beyond. So currently there are 1,000, well, about 1,200 PACE units installed by the end of March 2020. To date, around 4,500 units have been already installed under the German support program, the KfW 433. And then under an older EU-funded project called Anitil, which is the precursor to PACE, over 1,000 units were installed in that project. So altogether, plus or minus to date, around 10,000 units have been installed and are operating across Europe. And here you have a graphical representation of where you can find all the units and where they're clustered. Obviously, it's linked to many different reasons why fuel cell micro CHP is taken up in different markets, market conditions, support programs, regulation in place, footprints of the different manufacturers, and so forth, which you will learn more about in this presentation and further presentations. So I think this is important to point out. To date, over 350 million euros have been invested in stationary fuel cells or have been undertaken or planned over the next 5 years. So that represents about 30% of all the reported hydrogen investments in Europe. I should point out that those investments also include on the mobility side, but also some of it's in the mobility side. Excuse me. Here is an overview, an initial analytical report from the DTU in terms of the technology and its performance. To date, we've seen exemplary performance by fuel cells. I think the main takeaway is the availability factor, almost 99%, which means that 1% of the time they don't work, and that's usually for maintenance purposes, exchanging of filters and so forth, but they have a very reliable and strong availability factor. And as I mentioned at the beginning, depending on the technology and the availability, the efficiency ranges, total efficiency ranges can be quite high. Already through the project, we've been able to reach out to those customers who have decided to invest in a fuel cell micro CHP. The customer profile, a majority of them live in 2 to 4 person homes, although you do see them in the sort of commercial space as well, buildings, SMEs, and things like that. 95% of the respondents chose to purchase the units themselves, and for the most part, a majority, up to 90% of the customers own the building where they've invested in a fuel cell micro CHP. In terms of building types, 63% replaced the existing heating systems, 31% in addition to existing heating systems. Most of them, as I mentioned, are in the residential area, either homes or semi-detached. And for the most part, most of the buildings are relatively modern, if you consider 50 years modern. There are many different motivations to buy. I mentioned some at the beginning. A lot of it is linked to CO2, the whole climate change conundrum that we're facing globally, and in Europe, where we're aiming to be carbon neutral, net carbon neutral by 2050. It plays on many people's minds, and people want to take control of their own heating and electricity requirements, and also contribute towards the environment. So reducing CO2 emissions is important, saving energy, saving costs. 72% of the respondents would pay more for a micro CHP unit as an incumbent technology, which is interesting. And 50% would be willing to pay an additional 2,000 or more, assuming operational savings of approximately 30 euros per month and reduce carbon emissions by at least 20%. And as I mentioned before, the total CO2 savings hovers around about 30%. So as I mentioned before, there are significant CO2 reductions. So using natural gas, converting that into hydrogen, and then running the hydrogen through the fuel cell. So there is no combustion, which means there's no NOx is virtually eliminated. Particulates have been virtually eliminated. So local air is better for that. NOx, of course, is also reduced significantly. And here you have a comparison or an analysis that was recently done by Roland Berger, looking at annual CO2 emissions of different technologies from air heat pumps to internal combustion CHP, Stirling CHP, and then in the case of fuel cell micro CHP, you see about a 33% reduction in CO2, and in terms of NOx, a significant, if not virtually, elimination of that particular greenhouse gas. So in addition to those benefits, there is the point of system reliability and reduced risk costs. So if many people install a fuel cell micro CHP in a home, you avoid a lot of unnecessary upgrades in the power grids to distribute power from a more centralized source, I would say. And through the Ennifield project, a study was conducted by Imperial College that estimated that approximately 3,500 euros per kilowatt is avoided in terms of power distribution costs by micro CHP today and continuing into 2050. So this is a significant savings as well. And I think it's interesting to point out, because of this, micro CHP is not really competing with the likes of heat pumps. In fact, they complement each other because, let's say, in the wintertime, you have the seasonal effect. So Europe is cooler. So there's more need for electricity because many people also use heat pumps. Well, a fuel cell micro CHP unit will provide the heat for the home, and any excess electricity can help in terms of stabilizing the grid and providing that necessary additional power required by heat pumps. So they're not competing technologies at all. In fact, they complement each other. So in conclusion, and some recommendations before we move on to the next speaker. It's a no regrets choice. It's future compatible, meaning today, yes, fuel cell micro CHP can run on natural gas, but they can easily be converted to run on pure hydrogen in the future. So it is a future-proof technology in that respect. It's already supporting the reduction in greenhouse gas emissions, a third of CO2, and virtually eliminating NOx, reducing SOx and particulates. So a key contributor today and certainly in the future. It's fuel flexible, as I mentioned at the beginning, and technology neutral. And in the future as well, fuel cell micro CHP can be reversible, and as I mentioned, fully operated on hydrogen in the future. And it's an enabler. It allows for more renewables onto the grids. It allows plug and play or a mixture with heat pumps in the future, or today and in the future, especially as we find more electrification, especially in urban areas. There's certainly a role for such units to help in terms of the rollout of electric cars and so forth. But what we need today and what we need in the future is a stable policy framework, so we can create a level playing field for the technology to support the EU's decarbonization pathways. And we need a framework to ensure that the benefits of fuel cell micro CHP are also taken into account. So that was my final slide. I'm now going to allow my colleagues to give the moderation role to my colleague Jan Willem.
Yes, good morning, Hans. Thanks.
Hi, I'm Willem. This is Thomas from Coaching Europe. You're now the presenter, so you can start sharing your screen.
Okay. Let me. So can anybody see my screen now?
Yes.
Yes, we can see it.
Okay, good. Then I make it a little bit bigger so everybody can really see it. Thanks, Hans, for the introduction. There's a lot of things that you already pointed out that I will repeat, but like usual, as in school, repeating things are good so everybody remembers well. First slide. I will just tell you a little bit more about fuel cell technology and also about why we should use it in buildings. Of course, a lot of people know fuel cells from cars. In cars, mostly PEMs are used because of the low temperature and easy start and stop that PEMs allow. In buildings, you can use both PEM and SOFC, and we at Solid Power use the SOFC, which is a high efficiency and high temperature fuel cell. So it's a long name, combined heat and power generation with fuel cells, or fuel cell micro CHP. Basically, it's an energy or power plant for your home or your building. So it's on-site electricity and heat production for a building. It's very easy to install. It's almost like a gas boiler, though it isn't a gas boiler. It's not a specific heating system. There are different types, as on the sheet that Hans presented already made visible. There are systems that produce a little bit more heat. There are systems that produce more power, like ours, and especially the unit that produce more power than heat can easily be combined with heat pumps to provide the electricity for the heat pump, and the little heat will only used as domestic hot water. And that is mostly the way our units, the BlueGen units, are used. So easy to install. Of course, it's silent. Most micro CHP that we know from the past is used as with a combustion engine. So there's always noise, there's always rotating parts, there's a lot of heat dissipation, and also a lot of maintenance because of this rotating parts. Fuel cells work very silently. It's a chemical process, so there's no combustion and no noise, which is very convenient, of course, in a building. Outside a building, it's less important, but inside buildings, of course, noise is a very big point. They're very flexible and modular, so you can easily put 1 or 2 or 3 or even 5 units in a row to get a higher power or to serve your higher power demand. As Hans already said, it cuts energy costs. Because of the efficiency, it will reduce your energy bill. And as we see year by year, electricity prices rise, not the production price, but mostly taxes and renewable taxes on polluting carbon electricity from coal-fired plants and gas-fired plants. It is always rising, and of course, a big part is now being added with grid costs because expanding the grids for electrification also means a lot of extra cost for grid expansion, and that's what we see in electricity prices as well. So in most countries there are subsidies, and there's also tax deduction possibilities for these green investments in most European countries. So you can always check out your local possibilities for these kind of technologies to install in your building. Like Hans already said, it reduces your environmental footprint of the building, so it improves the energy label of the building, which is one of the musts under the EU legislation for buildings. And of course, when you use green gas, biogas, or hydrogen in future, you will have zero carbon units and a zero carbon building. Since there's no combustion, there's also no combustion products like NOx and SOx, only at startup and cool down in certain situations, which only happen maybe once a year or maybe even lesser. You will have NOx and SOx production because then fuel is burned to heat up the fuel cell before the chemical process can start. But that is really very little compared to combustion engines, of course. So only 1 day a year compared to all year long. Like Hans said, future-proof. Now we use gas from the grid to extract hydrogen from CH4, which is natural gas or methane. Also, methane can be biomethane, and from that we create hydrogen. And there, with that, electricity and heat. But I'll explain a little bit more from that on the next slides. This is a typical installation example of a fuel cell in a building. So most buildings, or almost every building in Europe has a gas connection, especially in cities and more densely populated areas. There is mostly natural gas, a good gas grid, and an electricity grid. Basically, you connect your fuel cell unit to that grid. Gas comes in, it creates hydrogen, you produce power for your lighting, for your heat pump, for your electrical domestic appliances. And of course, there's heat. And this heat can be used, if it's a lot, in your heating system. And if it's a little bit less, then you better store it in a buffer tank to provide domestic hot water for showering and doing the dishes, etc. And again, if you need more power, which we see a lot in Belgium at the moment, where electricity price is very high, up to a very high demand. So if you use up to 200,000 kilowatt hours, you pay the same high price as for only 5,000 kilowatt hours, so domestic use. So small and medium enterprises like bakeries, butcheries, etc., tend to put like up to 5 units into one cascaded solution, creating 6 kilowatts and over 70,000 kilowatt hours a year of power production. Local renewable power production. So just to point out the principle of a fuel cell. Fuel cells are already very old, discovered in 1800 something. So for that matter, not new. But of course, only now, say 10 years ago, we made commercially viable units out of it with the same principle. So we have oxygen from air that is blown into the fuel cell from the outside air. And we have hydrogen coming from natural gas in most current cases. And of course, if there would be hydrogen available, you could add that to the fuel cell directly. And in future, we will have models that can run on 100% hydrogen without having the whole reforming and hydrogen production processes inside of the system anymore. That's something that we can leave out then. So basically, there's always a membrane, so a piece of material that separates the oxygen from the hydrogen. And through that membrane, oxygen can migrate, meet the hydrogen, and then chemically convert into water, H2O. And at high temperatures, this will be steam, which will be cooled down in a heat exchanger. And that is the part where you also get your heat from fuel cell, which you can, of course, always use in a building. So that is the basic principle, which happens in one cell, one fuel cell. And what we do as fuel cell manufacturers, we produce cells and then we stack them all together to the certain amount of power that we think we can sell. So in most cases, it's between 700 and 1.5 kilowatts at the PACE project in the products. But of course, you can stack them up to higher amounts. So in future, we'll next year even already we will have the first 6 kilowatt prototypes ready. And a year later, we will have 6 kilowatt units for the market. So again, a little bit about why we use, or you would use fuel cell micro CHP. Well, first of all, because decentralized power generation is a lot more efficient than producing it somewhere far away and then transporting it through high power lines and transforming it up and down until you have it in your homes or buildings. So in this picture, 45 to 70% will be wasted at the coal-fired plant, or the older coal-fired plant would have a 30-35% efficiency. Newer ones 40-45%, and coal and gas-fired plants would have 55 to 60% electrical efficiency. So the rest is heat, which is not always used or mostly not used, but just lost in cooling towers and maybe cooling water of rivers nearby. Then you have your transportation losses, and only 25 to 40% of the original energy will enter your building to be used as electricity, and mostly not the heat. So if you do that at the building itself, you will have up to 90-95% efficiency, which can be up to 3 times more efficient. Just by doing it locally, and not even thinking about using pure hydrogen for renewable sources, which is of course the future. And that is what the lower picture looks like. So there will be a two-way energy stream from both production, local production, as local consumption in electric cars, heat pumps, etc. So fuel cells can contribute to this complete system, especially in winter times and when there's no sun and no wind, in this whole local energy system. So we don't need those big coal-fired polluting plants anymore. We can now do it all by ourselves in our homes and buildings. So my last slide. This is about the future, but this is already happening partially in Germany already. This is about the seasonality of energy consumption. And that is where fuel cells can also play a very big role. The purple arrows downwards are actually pointing into the future. So the pictures left and right above are still based on fossil fuels, so coal-fired plants and gas and oil coming from oil rigs. Then, of course, transportation will always be necessary, gas grids, electricity grids, and in the future they will contain biogas and hydrogen on the right side for the in the gas grid, and on the left side only solar and wind power from renewable sources in the electricity grid. And there will be a very big interaction between those grids. As you know, in wintertime, the sun isn't shining that much, only for a few hours, and therefore solar power in wintertime, so say 3-4 months, is very, very little or nothing, especially when there's snow on the panels, and also wind is sometimes less, and basically only half of the year we will have those renewable sources. So the other half of the year we should use stored energy from this renewable systems. We can obviously store that into molecules, into gas, and that gas would be hydrogen. And if you wish, you can even make from hydrogen methane again, synthetic methane we call it then. by adding CO2 from the air, and then becomes natural gas, almost again, methane, that you can easily transport and store in the grid. So what you do in summer, put hydrogen in the grid, take it out with your fuel cell in wintertime again, and then you can have your local energy again that you have stored in summertime from your solar panels. And that is what we can do all together with the enormous storage potential of the gas grid. I think we will wait with the questions, Hans, till later. So I've got some slides as backup, but mainly for questions. And I think time is already up. So let's go to the next speaker.
Yes, thank you, Jan Willem. We've already got a few questions, 3 questions.
Okay.
Just a reminder to all the participants that you can go to the chat function and you can type up your question. And as Jan Willem alluded to, we will take the questions towards the end. So we have one more speaker. So my colleague, Alexander from Cogen Europe, will just give a quick overview from a policy perspective, where fuel cell micro CHP is today and who or what we need in the future. If you bear with me for one moment, I will bring up the slides from my colleague. Here we go. Alexandra?
Yes, thank you, Hans. Hey. We can still see Jan Willem's slides.
All right.
I can try to show the slide myself. Oh no, now we have the slides. So as presented by Jan Willem and by Hans, there are very exciting developments in the industry side. So industry is investing enormous amounts of money towards the market introduction of the mass market adoption of fuel cell micro CHP. There have been quite a lot of pilots already showing the technological feasibility of the product. Now we have fuel cell micro CHPs on the market. The customer awareness is increasing. We're getting very positive feedback from the users of fuel cell micro CHP. On the policy side, we believe that we have an opportunity to deliver a successful Green Deal for Europe with stationary fuel cells as one of the key solutions to enable carbon emission reductions, to enable energy system integration and resiliency, and most of all, energy efficiency first. So we are now in the midst of a big debate on how do we, what do we put in the Green Deal? How do we ensure that Europe is on an ambitious pathway to carbon neutrality by 2050? And when it comes to the Green Deal, we want to ensure there's a systems approach, and we take into account electricity, heat, and gas systems, so the main energy carriers into account in an integrated way. If we do that, then we must ensure that stationary fuel cells are well accounted for and the full system benefits are taken into account across the different Green Deal components. So that's our main message for the Green Deal. But of course, there are other relevant files within the Green Deal where fuel cells are uniquely positioned to contribute. And so with the legislative process going on at the moment, we must ensure that the barriers are removed and also that the benefits of fuel cell micro CHPs are recognized. When it comes to the renovation wave, we know that's a priority. Buildings will be key in delivering decarbonization of the economy, relaunching the economy and ensuring a green recovery from the corona crisis. We as an industry, we are committed to delivering significant benefits to the buildings sector with fuel cell micro CHP. And therefore, for the renovation wave strategy, which is upcoming in June, we want to ensure a level playing field and foster a diverse mix of solutions. As has been presented already, fuel cell micro CHP can enable an efficient and renewable electrification. So electrification of end use and also the use of renewable gases and decarbonized gases are complementary, especially for the building sector. And so we must ensure that the renovation wave does not only refer to electrification as a solution, but it refers to the synergies that we can create between the different technologies and enablers in this respect. And we know that a lot of funding will be allocated to buildings. This will ensure that jobs are created in the local economy. And so we must ensure that some of this funding is geared towards the industrialization of innovative and state-of-the-art technologies like fuel cell micro CHP. Then a second key file that is very actively debated at the moment in the context of the Green Deal is energy systems integration. I hope that through the previous presentations, fuel cell micro CHPs, or it is clear that fuel cell micro CHP is a key integration solution. It brings together electricity, heat, and the gas systems, and it can also help ensure a higher integration of renewable energies. This is definitely an important aspect that we must take into account. And so in the context of the energy systems integration file, we do want to see an accelerated uptake of renewable and decarbonized gases, including hydrogen, and the applications of hydrogen must be taken into account for the building sector as well. There's a humongous potential on hydrogen and decarbonized gases in buildings. As Jan Willem mentioned, most buildings in Europe have connection to the gas grids, and distribution gas grids are well developed across Europe. So we must take advantage of that infrastructure and convert it to a more future-proof solutions like fuel cells. And in addition to that, we must ensure that those new gases, so renewable, decarbonized, and hydrogen gases are used efficiently, and that's where fuel cell micro CHPs can play a role. Another point that we'd like to highlight is this complementarity between the electrification of end use, especially when it comes to heat, and fuel cell micro CHPs. In winter especially, we will expect quite important peaks in electricity demand from electric heat pumps, also from electric vehicles. And so fuel cell micro CHPs, by producing both heat and electricity at the same time, are the perfect enabler of an efficient and renewable uptake of electrification. And then we have the hydrogen strategy. We know the Commission is now working on strategy on hydrogen economy. And again, we would like to highlight the important role of efficient heat use, efficient hydrogen use in buildings. We see an important role for hydrogen in buildings, and so the potential should be identified, and also at the same time we want to prioritize fuel cell micro CHP to boost the efficient use of hydrogen in buildings. Those are the key messages that we have for policymakers in the context of the Green Deal. And now I would like to revert back to Hans to open the discussion.
Thank you, Alexandra. So just a reminder to everyone again, you can use the chat function as part of the WebEx webinar to ask your questions. In the meantime, a couple of you have already found the chat function, and we have 4 or 5. I see my colleagues have already answered one of them online. Just for all of you who are not looking at the chat function yet, this webinar is being recorded. We will make it available on the PACE website, and all of you registered for the webinar will also receive a summary of the webinar with a link to the video and the slides. So don't worry about that. So I think Jan-Willem, you can answer most of these, and I can see on the list of participants, people joining, that some of our other project partners are on the line as well. So if there's something too technical for us, certainly they can help us. Maybe we'll start with the first one, Jan-Willem, if you can help us. Just to understand the commercial feasibility of a fuel cell micro CHP, how much consumption of natural gas what does one need to produce 1 kilowatt hour of electrical energy or 1 kilowatt hour of heat?
Yes. Okay. Well, this ties completely in with the efficiency, of course, of the fuel cell. If you take our fuel cell with a 60% electrical efficiency, from every 10 kilowatt hours of gas, so basically 1 cubic meter of gas, you could make 6 kilowatt hours of power and around 3 to 3.5 kilowatt hours of heat. With other fuel cell types, it might be vice versa, so a little bit less electricity and a little bit more heat. But basically, if you look at the spec sheet of the fuel cells, you look at the efficiency, and then you can actually just divide by the efficiency on the electrical and on the heat side to more or less calculate how much gas it will use. So in our case, to produce, say, 13,000 kilowatt hours a year, you would need 2,100 kilowatt hours of gas, and therefore around 2,000 to 2,300 cubic meters of gas per year to produce this 13,000 kilowatt hours of power and around 6,000 to 8,000 kilowatt hours of heat.
Okay, thank you, Jan-Willem. The next question is actually about price of the units. I don't know if that's something that you can discuss openly on the webinar, but maybe you can give a range. I mean, every country is different. Every country has different support schemes in place, so there's not one size fits all.
Exactly. It's not one size fits all, of course. So there's higher powered units, but the price of the 1.5 kilowatt unit in our reference country, Germany, is 25,000 euros. But of course, savings are very huge, and there's a lot of subsidies. So there are payback times between 5 and 7 years at the moment. Which is, of course, very good. And even in countries like Belgium, you could still have payback times of 7-8 years. And if you use a little bit less power or heat, it would be a little bit longer, up to 10 years. But basically, to produce 13,000 kilowatt hours of power with such a fuel cell, would need 15,000 kilowatt hours of 15,000 kilowatt peak on solar panels, and that's about 100 square meters. So I always compare it with solar panels in that case. So people see that fuel cells are a very compact way to produce power in buildings, especially if roof surfaces are small, because 100 square meters is a little bit much for most roofs. And of course, you still have the seasonal problems. But the price of 15 kilowatt peak solar is also around 20,000 euros. So from electricity or power production comparison, it's not much more money to spend on a fuel cell.
Thank you, Jan-Willem. That's a good point. And as I mentioned before, every country is different. So you have the base price of the unit, but then depending on the country you are, you might have an interesting spark spread. For example, in Belgium, the price of electricity is quite high. Jan-Willem mentioned that before. There are taxes associated with that, or different schemes, which makes the price for people like ourselves at home who are buying electricity quite high. But at the same time, the price of natural gas is relatively low and stable. So you have to take into account those aspects as well as different support schemes that exist across Europe at a, say, federal, national level, but also regional and even local level. And that actually goes into the next question. Maybe Jan-Willem, you'd like to address this. I think you know best Belgium, the Netherlands, and the UK, but I'm sure you know what's happening around Europe as well.
Well, it's constantly changing, but of course, there's in every country there's something, and in Germany there's even a lot. So there's many support schemes you can use, both from the grid provider, from green certificates for CHP, as feed-in tariffs, and also with KfW, a very good a capex subsidy upfront as soon as you have installed the unit. So yeah, it's a long story for Germany to actually explain this in detail, but please go to my German colleagues for specifics around it. But almost half of the investment will be returned in the first year, and then the rest can be earned back in the next 5 to 6 years in Germany. That's basically the story in Germany. In Belgium, there's a capex bonus of 2,500 for our unit at least. It ties in a little bit with the output of the unit. Yeah, unfortunately, in UK at the moment, there's not really a feed-in tariff anymore. There are some tax deduction possibilities and also some heat incentives still. And the focus on hydrogen becomes better and better. So we're still waiting for something good for fuel cell micro CHP in UK. But I'm pretty sure that 100% hydrogen units will be well subsidized in the UK in the near future. And as for the Netherlands, I saw some Dutch participants. There's some good tax reduction schemes like the EIA and the KIA. So those basically are renewable energy investment tax deduction programs, but there's no specific feed-in tariff or capex subsidy available in the Netherlands at the moment. So yeah, we can go to every other country, but let's not do that now. It's a bit complicated to go through all countries, but these are the main markets for us at the moment. So I want to keep it with that.
Thank you, Jan-Willem. A lot more questions are coming in, and just checking the clock as well. We have about 6 minutes. Let's see. Perhaps you can answer this one. What is the maximum temperature levels of the heat one can obtain from fuel cells that are commercially available?
Yeah. that's an easy question. So let's take that one. Sure. The temperatures inside of the fuel cell are very high, up to 750 degrees. So that's not the temperature that you'll see at your heat exchanger for your domestic use. So there's two heat exchangers inside of the unit. One heats up the incoming gas and air, and therefore it already goes down to around 120 degrees. Then it goes to a second heat exchanger, and that one's connected to your domestic hot water or your heating system in the home or building. And from that, you can take about 70 degrees or up to 70 degrees Celsius to put in your buffer tank or to use in your home. So it's high temperature water, so therefore very suitable to suit your domestic hot water consumption.
Okay, thank you. I think we have a seasonality question. So the energy flow of heat pumps in the winter, I guess how the two technologies complement each other. Maybe you can speak a little bit to that as well.
Mm-hmm. Yes, of course. What we see or what we will see is that the grid will be heavily, there will be a big strain on the grids in wintertime when everybody would electrify his home. That's not even possible in most areas and most rural areas because it will just overload. And then if you take electric cars with it, it will be even worse. So big expansion should be done on the electricity grid. And you could avoid that by putting a certain amount of fuel cells in that area. Of course, a heat pump takes away, depending on what kind of heat pump it is, of course, between 1 kilowatt and maybe 6 kilowatt, depending on the building. So, of course, a 1.5 kilowatt unit wouldn't fully be able to take that away. But if you consider multiple units and not heat pumps in every home, in the complete area, it will definitely take away a lot of the load and the strain on the grid. And of course, if you see it on a yearly basis, your production of 13,000 kilowatt hours a year will definitely will cover your heat pump demand, and of course the rest of the domestic demand. Not sure. I didn't really see that question, but so I don't know if I covered that question completely now, but I hope so.
Yes, I think so. Let's see, we have a few more minutes. So there's a question about CO2 emissions. So the reduction of CO2 emissions is given due to less demand from the electricity grid, correct? In countries like Austria, where the CO2 intensity of electricity is low, is there still potential to lower the CO2 emissions with the use of a fuel cell micro CHP?
Mm-hmm.
Potentially in combination with green gas or hydrogen.
Yeah, sure. If you use green gas and hydrogen, it will be carbon neutral, or almost close to carbon neutral. But even the decentralized benefits that I try to explain in one of my sheets definitely also apply here. So just by decentralized power production and not having to transport heat and power, you can, of course, already save up to 30% on carbon emissions. Just by doing it more efficiently at home and not even using renewable fuels, but just fossil natural gas, you could still, of course, go up to 50 or maybe even 60% just by doing it more efficiently and using all the heat in your building and not throwing that away. And of course, avoiding the transportation losses in the electricity grid by producing electricity yourself at home. So those two benefits of decentralized energy production already contribute to CO2 carbon reduction.
Okay.
Maybe if I can very quickly complement. what Jan Willem has just mentioned. When it comes to the energy mixes of different member states, we know that on average the electricity mixes are becoming more renewable and therefore more carbon neutral and less carbon intensive. But we have to look at the marginal plants that CHP and micro CHP displaces. And we know from several studies that have been carried out, which we can share, that micro CHP produces electricity that displaces much more carbon intensive power plants and less efficient power plants. So as we see more electrification, so additional electricity demand, that electricity demand will need to come from more efficient sources, which in this case would be fuel cell micro CHPs. So yeah, we rather than looking at the average power mix, we should look at the power mix in winter and the power mix that is really used for that additional electricity demand from electrification.
Thank you, Alexandra. There are a few more questions, but we don't have enough time to address them all. But we will share the questions with the different speakers, and we will try to incorporate them in our summary that we will send to all the participants. Before I wrap things up, I will just let my colleague Alexandra speak to this, or I can do it myself. PACE with another EU-funded project called COMSAS, also focusing on stationary fuel cells at a much bigger or industrial level. We've put together a declaration concerning a joint declaration concerning stationary fuel cells between the two projects, and you can find more information about the declaration on the PACE website. We'll include a little blurb about this as well in a summary to all the participants. It's about while recognizing and highlighting the important role of stationary fuel cells, small and large, and how they can contribute to the decarbonization of Europe and the goal to be net carbon neutral by 2050, looking at the European Green Deal and the past clean energy package and how these technologies can support these short, medium, and long-term energy and environment targets. So you can find more information on the PACE website. Signatories today include organizations, companies, individuals, research institutes, hopefully soon politicians as well, both national and European. So you can find more information about the declaration on the PACE website. And then finally, just for your information, this is not a one-off. PACE is organizing a series of different webinars focusing on different stakeholder groups. The next webinar will take place on the 16th of June, where we'll be looking at fuel cells in buildings, plug-and-play solution to reduce energy costs and emissions. And you'll receive more information probably by email if you're in our database, but you can also find more information on the PACE website. And then maybe finally, not included in this slide as well, but I can at least announce that during the EU Sustainable Energy Week, the PACE project is part of a group of different organizations that will be organizing an event on the 25th of June in the afternoon. So look out for more information about that as well. So a big thank you to Jan Willem and to Alexandra. Thank you for your contribution today. And then thank you also for answering many of the questions. And again, thank you everyone on the line for joining us today. I think we had almost up to 100 participants. So we're very pleased about all the interest in fuel cell micro CHP in the PACE project. So with that, I bid you all farewell and thank you. Hopefully we'll reconnect in another webinar at another time at another place. Thank you and good day.